Hello, my name is Raphael, and I will talk today about attribution consistency in time series foundation models. The research question was how similar are the input attributions of different time series foundation models on the same inputs. Let's break this down. I will first shortly talk about time series foundation models, and afterwards about what input attributions are. Time series foundation models are forecasting models that can predict the future of a time series, or that can fill gaps in an existing time series. They work in a zero-shot manner. That means they can predict time series even if we haven't trained on our specific data set. And this is possible because these time series foundation models are trained on massive data on very different and very big variety of data sets. And they are kind of similar to LLMs. The difference is they are not predicting the next token, but they are predicting the next time step. In this work, I looked into three time series foundation models and analyzed them. The first one being Morai 2. This is a patch-based transformer. Also, Kronos 2 is a patch-based transformer, which cannot only predict univariate but multivariate time series. And the third one is not a transformer, but a state space model called flow state. So, what is input attribution? I will read out the first definition. Attributions estimate the contribution of each input variable, for example a pixel in an image or a word in a sequence, to the final output of a neural network, of a deep neural network. So what does this mean? Let's assume we have a function f, which is a deep neural network, and this function takes as input an n-dimensional vector. Then the input attribution is also an n-dimensional vector, where each value corresponds to the importance of the input vector position. So A1 is quantifying how important x1 is, and so on. So importance is not clearly defined here. So one specific definition of this are saliency maps. Saliency maps are one way of quantifying this importance, and they do this by defining the attention by the derivative of our prediction function with respect to each input value. And for that we need a specific input. For example, an image if it's about convolutional neural networks, which is the domain for which saliency maps was first developed. So we take this image and then we calculate for each pixel how the derivative for this pixel is. Because if this is high, that means if we change this pixel, it will have a big impact on the output. An improvement of saliency maps is smooth grad. So in smooth grad, we're not calculating the saliency map once, but we calculate it multiple times, but each time with some noise added to the input image, and then we average over the entire set. And the interesting thing is we get a more robust output than with the saliency maps. So tiny changes that can make a big difference are often very locally, and if we add the noise, we can sort this out. You can see these animals. If we add 0, noise, we kind of can see the animal, but by adding more noise and running it multiple times, we actually get sharper images of the saliency maps. So I talked about images now, but what about time series? The cool thing is saliency and smooth grad are designed for images. However, they can also be applied to time series. This is what I did. So the first thing I want to show you here is with artificial input data. Let's take this function and take 512 time steps and predict the 513th. So if we apply Kronos for this and then calculate the smooth grad of that, we will see that the very last, let's say 20 to 30 values define probably the largest part of the prediction. So these are the most important values according to smooth grad, which makes sense, because after that is the next time step that we want to predict. And now I switched to Morai, and also if you use the Morai model, the smooth grad will also show you that the last values are the important ones. In this case, even less values are important here. If we switch now to the flow state model, we also see that most of the attention lies on the last values. However, we also have this repetitive pattern where some values in between are also important, and we also have the very first value be considered important by flow state. And this would make sense if this is because we have the same steepness here, the same gradient here. So this is what I first thought, that maybe flow state focuses here because we have the same gradient here and here. However, you will see in the next function that for Kronos again, we only focus on the last values. For Morai again, we focus on the last values. But for flow state, we have to focus on the last values, but also on the first value again. And I don't really, for me, it's not really clear why flow state focuses here on the first value as well. To look into more time series, I decided to evaluate this on real data. So let's take 3 data sets. The first one being the ITITH1, which is a hourly sampled electricity transformer data set. The second data set, this is public, is also a public data set. It's a weather data set where each time step is a 10-minute jump. And the third one is DigiSeal. We added this to this study because DigiSeal is unpublished. So we can be sure that those foundation models that I look into are not trained on the DigiSeal data because we haven't published it yet. DigiSeal is a data set we recorded over multiple months of a mechanical seal. We recorded vibrations, temperature, and rotation speed. And it's recorded in a research project, which is also called DigiSeal, funded by the Bavarian Collaborative Research Program. Our partners at DigiSeal were Igel Burgmann, Molkerei, and Hochschule München. And us being Fraunhofer MFT. So what I did next is I wanted to take these 3 data sets and then calculate for many different 512 time step windows and predict the next value, and calculating the attention or the attribution of the input and then averaging over all windows. And if I look at ITITH1, which we remember was this data set where each time step is exactly 1 hour, we get this attribution where we have the periodicity of 24, which makes sense because electricity has this periodicity of dailiness, so each day we have probably same patterns, and all of the three models agree here that every 24th value has high importance, while the other values are not that important. If we look into the next datasets, into the weather, we see a different picture. Kronos and Moray just focus most on the most recent values, and then they fall down and stay at a low level. Flowstate also focuses more on the last values than the other ones. However, it still has this repetitiveness of every 24th value being of most importance. And for me this is strange, because if we show here the time step deltas, we have 10 minutes, and 24 times 10 minutes is not really a structural pattern in weather data. And the same applies for DigiSeal, where we have a 3-minute delta between each time step, and also in this case Flowstate assumes a repetitiveness of 24, so it assumes that every 24th value is most important for predicting the next time step, while Kronos and Flowstate only focus most on the most recent values and then give less and less attention to the rest. So I believe that that Flowstate is overfitted on training data where this 24 time step interval actually applies. So I think this is how Flowstate could improve, by providing more diverse input sampling rates. The next step that I want to share with you is how similar the attributions are if we calculate them with the Pearson correlation. So if we look at the ETTH1, we already saw all three models have very similar attention values, or like attribution, input attribution, and therefore we also have very high Pearson correlation if we compare the three models. If we look at the weather data, it looks quite different. So the Flowstate model seems to be very isolated, which makes sense because it looked different than the other two models, but also Kronos and Moray are not that similar, at least not as similar as they were in the ETTH1 dataset. For our unpublished data, the DigiSeal vibration, we have a quite high Pearson correlation again, showing that despite Flowstate having these 24 time step patterns that the other ones don't have, we still have an overall similarity in how the input attributions are distributed. One thing that I talked multiple times now about is that I look at how much of the overall attribution lies in the last time steps. And for that I decided, let's look at the last 32 time steps of these 512 time steps. If we would assume that we have a completely evened out attention, then we would have this value that is dotted here in gray. However, for every of the three datasets, with every of the three models, we have way higher attribution of these first 32 values. And this makes totally sense, in my opinion, the last 32 values, because the last values should be what we have to look out for if we want to predict the next value. So what have we found out? I just talked about that the recency is of a big importance when it comes to what influences the output. The second thing is that both transformers have more similar attention patterns than if we look to the Flowstate model. I also have the strong assumption that flow state seems to overfit on a periodicity of 24 time steps. So it kind of assumes for every data that you give him that every 24th value is more important than the values in between for predicting the next time step. So overall, I can say that smoothcut helps to understand how time series foundation models analyze or interpret or focus on the data, and this can help to design new time series foundation models that actually focus on the most important parts of a time series. Thanks for your attention.